Okay, well here we are with STAWA set 20, balancing redox equations. And this is really putting together your skill sets from sets 18 and 19 all together in one package to solve this very useful task of balancing a redox based equation. And this is one of the most useful skills, especially in more difficult and more complex types of equation, which are very prone to make errors with when you balance by hand, but sometimes work beautifully easily with this technique. So our approach requires two sorts of things. Firstly, what we've got to do is we've got to identify the two parts of the process, the reduction and the oxidation. And we can see here that what's happening in this case is that bromine here is going to be reduced to the bromide ion. Okay, that's the actual reduction. Reduction is of course the gain of electrons, so we need to put electrons in there. We need to do all the usual things that we do for balancing these sorts of equations. So first off, what we need to do is balance out the atoms involved. That's very easily achieved like that. I'm just going to tidy up this so that it looks somewhat more like a chemical equation and somewhat less like a dog's breakfast. There you go. Beautiful. There you've got your reaction. So on this case, the bromine's being reduced. On the other case, the iodide ion is actually being oxidized to iodine. Again, I'll tidy those two up and we can look at that. Okay, iodide going to iodine. Houston, we can see immediately that we have a problem here. The problem is that the atoms aren't balanced. To do that, we need two iodide ions to make one iodine molecule, and in doing so, the two electrons from here are made available. In other words, the iodine is oxidized. Now, what we do to together with that, let's have a check across there. One electron. Oh, we're going to need two electrons there. Okay, so there we are. The bromine needs two electrons, Br2 to Br minus. I'd written it for one, now it's done for two. Iodide minus to I2, that also releases two electrons. You can see that what happens is that here and here, hang on a second, here and here, they cancel each other out, don't they? If I put two electrons on one side and take two off the other, then of course the things cancel out. So once they cancel out, we can do that. Just knock them out. Okay, and overall, which is my way of saying balanced, we have we're going to take one of our Br2s. We're going to take our 2I minuses, two iodides, okay, and what we end up with is going to two bromides, and of course an iodine molecule, and that's over there like so. So now what we can see, what's happened overall here, we've got a balanced equation. It's electrically balanced, all the elements are balanced, and that's just nicely done. And I'm sure you could have done that just by looking at it, because you've been doing those things since year 10. But this is the way to do it, using the electron transfer. You just make sure that the electrons balance up and scale the two half equations so that they do. In this case, that wasn't necessary because one produced 2i minus, and the other two electrons, and the other produced 2 electrons, and so overall there was no issue with it. That one worked easily. The next one, of course, is more interesting. Question 2. We need to again go through our process. In this situation, we've got copper reacting with silver ions to produce copper 2 ions and silver metal. You might say that a blue solution slowly becomes colorless, and a colorless solution slowly becomes blue and forms a silvery grey precipitate. As an orange solid added to it disappears, or something like that. We have actually seen this guy before. In other words, copper is displacing the silver. So the two half reactions that we've got here are, firstly, the copper is being oxidized, and of course when that happens it is making available 2 electrons to something, so it's giving up its 2 electrons. Let me just get into there. I'll just sort this. I'm experimenting with a larger font on this particular video than some of the earliers to make it easier to see, but of course it makes it look a little bit horrible initially, and so I have to be a bit more careful with my font formatting quickly. Okay, so the copper's being oxidized. What's happening to the silver? Well, our silver is actually being reduced, and what's happening in that situation is it's forming solid silver. To make it do that, we need to add an electron. So when we add an electron to the silver, it forms the silver metal. Okay, now what do we need to do to make that look good? There you have it. So this one here is going to be the ox, and this side here is going to be the reduced. Okay, now we can write a balanced equation for it. But note, we do this by looking at these electrons. We only get 1 electron used up for each silver, but for each copper we need to have 2. We need to produce 2. So the oxidation reaction here produces 2 electrons that need to be got rid of. This reduction only produces 1. So a problem you're familiar with. How do we make 2 into 1? Well, we scale it by 2. So what we would do in this particular case is we time this equation by 1, and we would times this equation by 2. Okay, that makes 2 electrons available now to be used up by silver, and when we do that, our overall equation is copper times 1 plus silver. Here's our silver. But note, we said we're going to times this by 2, so we do that. And that will form for us copper 2 plus. Well and good. But also, and silver. Let's put the plus in there, and the silver there. But note, we said we needed to scale the whole thing by times 2, so we also need to scale that silver. Now we have a balanced equation on this particular thing. And you can see that this is, say, copper metal plus silver ions, 2 silver ions, produces a copper 2 plus and 2 silver. Let's check to see that it's all worked out. One way of doing this is looking at the charge. 2 times plus 1 is 1 times plus 2. Okay, hunky-dory, everything works beautifully there. That one is a balanced completed answer. Let's put an underline underneath it. Okay, let's have a look at this one. This is a very easy one. This is the reaction of magnesium metal with lead salts. This is probably quite a good way of recovering lead salts, stop them from going to be released to the environment. If you had, say, some lead nitrate, I think what our lab ladies actually do is they throw a little bit of magnesium into the solutions of waste, the nitrate, and what happens is that they collect the lead, and then you can just pour the water down the sink. Well, that was the old way of doing it, at any rate. Okay, need to see what happens here. Two things. Magnesium is, of course, being oxidized to magnesium 2+. Please excuse me while I thieve. It's much easier to thieve than it is to write again. Of course, if that happens, then what happens is that we also release 2 electrons. Beautiful. Okay, and this, of course, because what's happened, we say oxidation is loss, reduction is gain. This magnesium is being oxidized. Okay, on the other hand, what's happening, we've got lead 2+, lead 2+ over here, is forming solid lead. Now, to convert a 2+ ion to lead with an oxidation of +2 to lead with an oxidation of 0, you have to add to it 2 electrons. And that's what we're going to do. And of course, if we're adding electrons, if it's gaining electrons, it is, of course, the reduction side of the reaction. Very, very simple and straightforward here. We just simply add those two together. We notice on this that these two over here, let's highlight them. Those two guys there, what happens is that 2 electrons appear on this side, 2 electrons appear on this side. They're therefore balanced with respect to electrons. All we need to do to make this one work is to copy down the reactants, and sure enough, we do that, and we find that we have, let's grab from here, makes life easier. And then we have our plus lead. And you might say to yourself, well, in that particular case, it looked like it was pretty well balanced to start with. We didn't really need to do anything. Nothing changed on that. But it shows the overall process for you. There's your answer. With more complicated examples, that is useful. Okay, I'll do the next 3 in another little block of video. Thank you for your attention.